Welcome back to Very Ordinary Differential Equations. In this lecture, we continue our review of series, turning our attention to power series. Once again, this should not be your first exposure. This is just a quick review. Well, what is a power series? If I take the sum, not just of a sequence AI, but AI times x to the I power, okay, that's a power series. Each term of the series is given by a sequence AI, but also a power of a variable x. Depending on the value of x, this series may or may not converge. If I change the value of x, I've changed the value of the terms that I'm summing up, and that might affect things. So when it does converge, the value the series takes will also naturally depend on the value of the variable x. So if we have a power series that converges, it's converging to something that depends on the value of the variable. In other words, it's a function. When a power series converges, we can write it is a function of x, or we can write f of x is the sum of ai times x to the I. Power series have a notion called the radius of convergence. Suppose the coefficients ai are given. It becomes very important to answer the following question. For which values of x does the power series even converge? Now, f of x was written as this power series ai x to the I, so we're actually asking for which x's does this function even exist? Well, here's the series f of x. It's the sum of ai x to the I. There are basically three possibilities for where this function converges. It might converge only for x equals 0. Now, when x equals 0, for the index 0, we do have some ambiguity because we would get 0 to the 0 here. In the context of power series, however, 0 to the 0 is just going to be taken to be 1. However, when the index is positive, so the index I is 1, 2, 3, and so forth, if x is 0, we get 0 to a positive power, that's just 0. So regardless of what ai is, if x is 0, we're just summing up infinitely many zeros here, and that's not hard to see converges. So the series will always converge when x is 0, but maybe that's the only x for which it converges. Alternately, it might actually converge for every x. It's possible that the AIs are chosen in such a way that for every x, this series converges to something. Or there might be a positive number r, so that when the absolute value of x is less than r, the series converges. When the absolute value of x is bigger than r, the series diverges. And exactly when the absolute value of x equals r, in other words, when x is r or minus r, maybe the series converges, maybe it doesn't. This is another possibility. But these are, in fact, the only three possibilities. Maybe a power series only converges at 0, or maybe a power series converges for all x, or there is this r that represents a strict interval on which the power series converges, outside of which it diverges. In this third case, we say that the radius of convergence is r. And in some contexts, the first situation is said to have a radius of convergence 0, and this one is said to have an infinite radius of convergence. Let's talk about centers of power series. The interval on which a power series converges is therefore centered at x equals 0. If we do a change of variables and we replace x with x minus c, we just get a new power series. I've replaced all of my x's with x minus c. The change of variables simply has an effect by shifting all values c units to the right. Now, there are three possibilities. Instead of converging only at 0, maybe it converges only at c. It might converge for all real numbers, or there is now a positive r, a radius of convergence, so that instead of talking about the absolute value of x being less than r, we talk about the absolute value of x minus c being less than r. This corresponds to an interval from c minus r to c plus r. Then let's take a look at some examples. Determine for which values of x the following series converges. Now, because the terms of this series have various powers in it, the ratio test is going to be a useful way to go. So what we do, we take the limit of the absolute value of one term divided by the previous one. Now, ai plus 1 is going to give us x to the I plus 1 over I plus 1, 4 to the I plus 1. Then I have to divide by this term, so this I 4 to the I ends up in the numerator, and this x to the I ends up down in the denominator. So after some algebraic simplification, here is ai plus 1 over ai. And at this point, a lot of stuff cancels. Okay, x to the I plus 1 over x to the I leaves just an x in the numerator. 4 to the I over 4 to the I plus 1 leaves just a 4 down in the denominator. But now I fundamentally have a constant x over 4 that I can factor out of this limit, leaving behind just the limit of I over I plus 1, and that limit is 1. So ultimately, the limit of the absolute value of ai plus 1 over ai is exactly the absolute value of x over 4. By the ratio test, this converges absolutely when that ratio is less than 1. In other words, when the absolute value of x is less than 4. It diverges when that ratio is bigger than 1. In other words, when the absolute value of x is bigger than 4. But the ratio test will be inconclusive when that limit is 1. In other words, when x is plus or minus 4. So we still don't know whether the series converges for x equals exactly 4 or minus 4. So we're going to treat those two cases as separate cases by specifically putting in x equals 4 and then x equals minus 4. If x equals 4, then our numerator becomes 4 to the I, which cancels the 4 to the I in the denominator, leaving just the sum of 1 over I. That's a divergent series by the p-test. This is the harmonic series, which diverges. But if x equals minus 4, then we get negative 4 to the I over 4 to the I, which simplifies as just negative 1 to the I. This is the alternating harmonic series, which we already saw in a previous video does converge by the alternating series test. Altogether, what did we determine? This series converges when the absolute value of x is less than 4. It diverges when the absolute value of x is bigger than 4. It diverges when x is exactly 4, but it converges when x is exactly minus 4. Therefore, the interval from negative 4 to 4, including negative 4 but not including 4, is exactly the interval of convergence for this series. As a second example, let's determine for which x the series converges, where we are summing up I squared x to the I over I factorial. Again, we're going to apply the ratio test. So we take the limit of ai plus 1 over ai, which after some algebraic simplification is just I plus 1 squared x to the I plus 1 times I factorial over I squared x to the I plus 1 factorial. And now we notice that x to the I plus 1 over x to the I simplifies to just being x, and I factorial over I plus 1 factorial is just an I plus 1 down in the denominator. But now I've got I plus 1 squared over I plus 1, so I can cancel one of those out. Also, the limit is as I goes to infinity, so this x is a constant. It can be factored out from this limit, leaving behind the absolute value of x times the limit as I goes to infinity of I plus 1 over I squared. But that's 0, regardless of x. That limit being 0 makes this work out to be 0. So by the ratio test, because this turned out to be 0, we got absolute convergence where x was irrelevant. So this converges for every values of x. It converges on the entire real number line. And as a third example, let's determine for which x this series converges. I factorial times x minus 3 to the I. Again, we're going to apply the ratio test. Anytime you see factorials show up, you should probably be applying the ratio test. So ai plus 1 over ai works out to be this, which after some algebraic simplification is the limit as I goes to infinity of the absolute value of I plus 1 times x minus 3. When x is 3, every term in that limit is 0. So the limit is 0, and therefore the series converges. But when x isn't 3, the constant x minus 3 can be factored out, leaving behind just the limit of I plus 1, which goes to infinity, and therefore the series diverges by the ratio test. So the only value of x for which this series converges is exactly 3. Altogether, what have we discussed? A power series is a series, but instead of just summing up a sub I, we are summing up a sub I times x minus c to the ith power, where c is called the center of the power series and it's a constant, but x is a variable. So depending on the value of this variable, the power series may or may not converge. We end up with an associated radius of convergence r. This is a radius of an interval on which the power series converges, centered at c, and this radius of convergence is typically going to be determined through the ratio test. If this radius of convergence is 0, that means the series converges only at the center of x equals c. If the radius is infinite, this is equivalent to saying that the series converges for every x. Or there may be a non-zero finite number r. Therefore, the series converges when the absolute value of x minus c is less than r, diverges when the absolute value of x minus c is bigger than r, and specifically when the absolute value of x minus c equals r. In other words, when c plus or minus r is the value of x, those two specific values will generally be tested separately to determine whether or not the series converges there.